Okay, we're going to look at solving the system of equations using matrices, homework. And so the first question is asking, what is the goal when you are doing the row operations and putting the matrix into row echelon form? Well, your goal for row echelon form is taking your matrix and getting the diagonal of 1, so it could be a 2 by 2, 3 by 3, or bigger, and getting zeros down below. And then you would get just numbers up above. And you've written it as an augmented matrix. You also have those constants. And so this is the goal that you want. Now when you're using Gauss-Jordan elimination, you go a little bit further, so that's why it's called reduced. So again, if it's a 3 by 3, we'd get our diagonal of 1s, zeros down below, but we also get zeros above. And then you can just see the answer to your system without having to do the back substitution, which is what you would do in the first one. For question number 2, we want to decide which row operations were used on the augmented matrix. Write the operation above the arrows. So let's see. To go from this first matrix to that matrix, it looks like all that changed the rows. So we have row 1 and row 2 interchanged. For the next one, it looks like we have a 0 now in that first entry. So to make -3 go away, we would have needed a +3. So 3 times row 1 plus row 2, looks like that would make our new row 2. So let's just kind of double check that that works. So 3 times 1 is 3, we get a 6 and a 15. We add, so that was 3 times row 1. We add row 2 to that, that's -3, -5, -13. And we get 0, 1, 2, which is exactly that. Perfect. So then it looks like it's changing. Just the 2 turned into a 0. So we're going to make 2 go away. We need a -2. So we'll multiply the other row by -2 because that has a 1 in it. We add that to row 1 to make our new row 1. So to check that that works, let's see, -2 row 2 would be 0, -2, -4. Row 1 is 1, 2, 5. We're going to get 1, 0, 1, which is exactly what we have there. So then it says, what's the solution to the original system of equations? Well, you can see the solution right here if we rewrite it into equations. X equals 1 and we get y equals 2. So that will be 1, 2. All right, looking at number 3, we want to solve it using, it says either Gaussian or Gauss-Jordan elimination. So it really depends if you want to do the back substitution or not. So looking at it, I have 2x plus 3y equals -13. I want to, let's see, let's rewrite it as the augmented matrix. So we get the 2, 3, and the -13, and then for the x plus 4y equals -14, we'll put 1, 4, and -14. So I've just made my augmented matrix. Now I see a 1, so without doing much work, I'm going to interchange those rows. So row 1 and row 2 are going to interchange. So I'll have 1, 4, -14, 2, 3, -13. And so then my next step is to try and make that 2 turn into 0. So that will go away with a -2. So I'll do -2 times the other row plus the row 2 to make my new row 2. So if I multiply the top row by -2, just a little side work here, -2 would happen, then I'll get a -8 and I'll get a 28. Add 2, 3, -13 to that, we'll get 0, -5, 28 minus 13, we'll get a 15. So my row 2 would be 0, -5, 15. My first row staying the same, 1, 4, -14. So then my next step would be to try and make the -5 turn into a 1. So when I want to make a 1, really that's multiplying by something. So I'm going to take row 2 and multiply it by, let's divide by -5. So that'll be multiplying by -1/5. And that will make my new row 2. So that will turn into, the first row staying the same, 1, 4, -14. The bottom row would be 0, 1, and then -3. So at this point, you could say, okay, we did Gaussian elimination, and I'm going to rewrite the system into equations and back substitute, or you can keep going. So I'm going to keep going. I'm going to use the Gauss-Jordan elimination. Basically, all that means is one more step in this case. I need to make the 4 become a 0. So to make 4 go away, we need a -4. So -4 times my row 2, add that to row 1, and that makes my new row 1. So my little side work here will be 0, negative 4, 12, because that's negative 4 times row 2. Add 1, 4, negative 14 to that. We'll get 1, 0, negative 2. So this becomes 1, 0, negative 2. I have 0, 1, negative 3. And so now just looking at it, since it's in reduced row echelon form, I get my x value is negative 2 and my y value is negative 3. I've solved the system. Okay, let's look at number 4. Again, it wants us to use either of those, Gaussian or Gauss-Jordan elimination. So I'm going to rewrite it as an augmented matrix, negative 3, 11, 1, negative 3, 58, negative 16. Again, I see a 1, so I'm going to interchange row 1 and row 2. So that's 1, negative 3, negative 16, negative 3, 11, and 58. Now I want this guy to be a 0, so it needs a positive 3. So 3 times row 1 plus row 2 will make my new row 2. And my little side work, 3, negative 9, negative 48 will be my new row 1. Well, not new row 1, but what I'm going to use. That's my 3 row 1. I'm going to put negative 3, 11, and 58 with that. So then that makes a 0, a 2, and a positive 10. So my system will be 1, negative 3, negative 16, and then 0 to 10. My next goal is to make that 2 turn into a 1. So I'm going to take row 2 and multiply it by a half to make my new row 2, which will be 1, negative 3, negative 16, 0, 1, 5. So if I stop now, that's using just Gaussian elimination, and then I'll use back substitution. So I'm going to stop this time, but if you want to keep going, your next goal would be to make negative 3 become a 0. So right now I know that my y value is going to be 5, and from the top equation I know that x minus 3y equals negative 6. So the back substitution is plugging that 5 in, so I get x minus 3 times 5 equals negative 6. That's x minus 15 equals negative 6. Add 15, and we get x equals 9. So I have a 9 and a 5. So my answer is going to be, let me undo that, it's going to be 9, 5. And again, you can check that you're correct by plugging that in, and it's supposed to satisfy both equations. Okay, we're going to look at number 5, which is a system of 3 equations. So we're going to have a matrix with 3 rows. So it'll be negative 2, 4, 1, 7, 4, negative 13, 10, 17, 3, negative 9, 6, and 9. And so we want to solve this by using either Gaussian or Gauss-Jordan elimination. Now, I don't see a 1 in my first column, so remember our goal is the 1's in the diagonal and then the 0's below. And so I can't interchange any rows to make that happen. I don't really want to divide. That would make a lot of fractions going on. So there's a couple different things I could do. Actually, I look at this third guy, and that one could divide by 3 pretty nicely. So I'm actually going to interchange row 1 and row 3, and then I'm going to take 1/3 of that. So that would become 3, negative 9, 6, 9. The 4, negative 13, 10, 17 still stays. And then I have negative 2, 4, 1, 7. And so if I take 1/3 of row 1 to make my new row 1, that would get me my 1, negative 3, 2, 3. So that's kind of a simpler way of getting the 1 instead of just dividing, because otherwise we'd have a lot of fractions to deal with. So now that I have that 1, I want to make my zeros down below. So let's work on making that 4 turn into a 0. So I need a negative 4 times, let's use that first row, that 1 I just created, add that to row 2 to make my new row 2. So again, the only row that's changing is row 2. So row 1 is 1, negative 3, 2, 3. Row 3 is negative 2, 4, 1, 7. And so my second row, I'm going to write my little work down here. Negative 4 times row 1 will be negative 4, positive 12, negative 8, negative 12. Row 2 is 4, negative 13, 10, and 17. So we'll get 0, negative 1, 2, positive 5. 0, negative 1, 2, positive 5. So then next, I want to make the -2 become a 0. So to make -2 be a 0, it needs to add to a +2. So I'm going to take 2 times row 1, add that to row 3 to make my new row 3. So my little side work for that would be 2 times row 1 is 2, -6, 4, 6. I'm adding row 3 to that. That's -2, 4, 1, 7. So I'm going to get 0, -2, 5, and 12. So my matrix, again, row 3 is the only one changing, so I'm going to leave the other 2 rows as they are. And my third row is going to be 0, -2, 5, 12. Okay, so the next thing that we want to do is make sure we have a 1 for the second part of the diagonal. So that's a -1. So to turn that into a 1, really just need to multiply by a -1. So -1 times row 2 to make my new row 2. And so my other rows will stay the same. So 1, -3, 2, 3, 0, -2, 5, 12. So the only thing that changed was the middle row to become 0, 1, -2, -5. And so the next thing I want to do is make a 0 down below there. So to make -2 go away, I need a +2 times row 2. I'm going to add that to row 3 to make my new row 3. My little side work here, 0, 2, -4, -10 is double row 2. Add to that row 3, that's 0, -2, 5, and 12. So it'll be a 0, a 1, and then a 2. So then my matrix will be row 1 will stay the same, row 2 stays the same, and then row 3 will be the 0, 0, 1, 2. So if I stop right now, that's Gaussian elimination. And I could keep going and try and make these guys into zeros, but I'm going to stop now and look at this row echelon form matrix and write my system. So this is going to be x minus 3y plus 2z equals 3, and y minus 2z equals -5, and then z equals 2. So now that I've kind of reduced the system, I can solve that by back substitution. So I already know z equals 2, that's one of my variables. Plug that in for my other z there. That's 1 minus 2 times 2 equals -5. So y minus 4 equals -5. Add 4, y will equal -1. So now I have my y. So I'm going to take both of these now. There's my z and my y. And I'm going to have x minus 3 times -1 plus 2 times 2 equals 3. That's x plus 3 plus 4 equals 3. X plus 7 equals 3, minus 7, x equals -4. So my final answer, just kind of putting that all together, will be an x value of -4, y value -1. Oops, and we have a z. Can't forget z. It was a system of 3 equations here. And that would be 2. And so if this is really the answer, it needs to check in all 3 of the original equations and make a true statement. So you can double check that. All right, so looking at number 6, it wants us to consider this matrix. 6, 11, -4, 1, 2, 5. Okay, so we want to identify 2 row operations that could be used to obtain a leading entry of 1 in the first row. So one thing that we could do is just interchange row 1 and row 2. Another thing that we could do is just divide the first row by 6. So if we take 1/6 of row 1 to make the first row, that would work. Now, which one would be easiest? I think that the first one would be easiest, so then we don't have fractions. So make sure you explain that. I mean, you can work with the fractions, but if you can kind of rearrange the equation and do some things like that, it's going to be much easier for you to keep going. All right, for number 7, this is a little review. It just wants us to find the asymptotes of this rational function. So remember that we have vertical asymptotes, and we also have horizontal or slant. So I know that I do not have a slant, because slant only happens if the numerator is 1 more than the denominator, and we don't have that. In fact, we actually have that the denominator is growing faster than the numerator. So when the denominator is bigger like that, it's a higher degree. The fraction actually, this guy right here, if the bottom's getting really big while the top is staying smaller, as x gets really big, our y values are going to get really small. They're going to go to 0. So we have that y equals 0 will be our horizontal asymptote. Now the vertical asymptote happens when the denominator equals 0. It's when our fraction is undefined. And so our denominator here is x squared minus 9, and it's equal to 0 when, well, we could factor it or we could solve, but it's x plus 3, x minus 3. So we get x equals negative 3 and positive 3. Those are our two x values. When I said or solve, we could have added the 9 over and solved the quadratic equation by taking square roots. Still, we get plus and minus 3. So those are asymptotes. Our vertical ones are x equals negative 3 and 3, and our horizontal is y equals 0.